and transcription, starting recording and transcription. My hope is to maybe turn this into a YouTube video as a future resource. Assuming it's not too terribly embarrassing, I might go ahead and start an iGEM YouTube channel. Thought that might be interesting. So for the students who are here, I hope you have VCell installed. Does everybody have it installed?
Yeah.
All right. All right. All right, good, good. And so what I'm going to do here is I've got maybe 5 slides. This isn't going to be a lecture. This is going to be interactive. So I'm just going to do a little bit about the history or sort of the background of what we're trying to do here. And then we're just going to open up the app and we're going to start building the model. I'm not going to go into a whole lot of detail about what's working behind the model unless you really ask. But the important thing is to try to get a model up and running today. So let me go ahead and switch over to presentation mode just real quick. Okay. So if you've just downloaded VCell, you also have to register and create an account. VCell is really neat. A lot of the problem solving and computation is done on the University of Connecticut servers. So you can run really big problems and it's all on their computer. So it's kind of unusual. So you don't have to have a real fancy computer to run it and do solutions. They will actually run it on their supercomputers for you. And they will also, they maintain a database of all your models. So you basically save your models on their remote servers. You know, you don't even have to take up any hard drive space on your own computer. Okay, so what are we going to do? While everybody starts up VCell and logs in, let me just say a few words. So the main thing I want to do is build this construct that Douglas and everybody's been talking about. So this is sort of the heart of the model that we're going to try to put into bacteria. So for those who aren't super familiar, I certainly wasn't familiar with how these constructs are sort of mapped and until last few weeks. That's one of the reasons I'm participating is because I want to learn how to do genetic engineering myself. So anyway, so we start with a constitutive promoter, okay? And then next to that is a ribosome binding site. Okay, so that means that the thing after is going to be turned into a protein. That's LuxR. And we'll go into what each of these do. And then we've got a stop codon. So that basically stops the RNA polymerase. So then we've got another promoter. This is our infamous prmA. This is the one that we're hoping is sensitive to PFASs. And then we've got a binding site for RBS again. And then we're going to make this LuxI. It's not an L, it's an I. And then we're going to stop. Okay, so then we've got a third promoter, which is pLux. And we'll go into how each of these are activated in a minute. And after pLux, we make the GFP protein, green fluorescent protein, and then it's a stop. So this is the construct, and the idea is that we're going to create a model that shows how this would behave in bacteria. And so while we do that, we're going to learn how to run simulations in VCell. We're going to analyze the results. And then this is a very iterative process. One of the bad things about biology so far is that a lot of these rate constants aren't really well measured or characterized. And that's sort of a big weak point when it comes to computational cell biology. It is a fun area. So it lies at the interface between all these different disciplines. And it's got huge potential. So there are a number of groups, including there's OpenAI, and then there's the British group. I forget what deep something, deep. Anyway, it's a British company. One of their big things is to automate the creation of these biological models. So that you just type in, create a model of the Krebs cycle, for example, in this organism, and it would put together a model for you. And this is great because in the age of omics, where you have tons and tons of data it's collected in parallel, then you can take this data and feed it into your models, and you can forward propagate and you can back propagate. Hi, Douglas. I'm so glad you made it. Okay. Let's, without further ado, let's switch over to VCell. So when you open it up, can you see my VCell?
Yeah.
Oh,
Yeah.
and okay, yeah, and I expect to be interrupted regularly. Okay, please interrupt. This is very interactive. Please interrupt me regularly when you have any question. So when you open it, it should look something like this. You'll have sort of a blank canvas here. And you've got the stuff on the left, which is sort of your kind of symbolizes your workflow on the left. So what we're going to do is we're going to put in the components in the model, and then we're going to go down here and build an application, which is actually a running model. And then what we're going to do is we're going to sort of iterate through that process. So actually, I do have a little slide on that. Yeah, so here's the workflow. So what we're going to do is we're going to input the basic building blocks, the molecules. We're going to define the structure of the model, the sort of physical structure. We're going to be doing a model that doesn't have any spatial elements to it. This is called a non-spatial model. And what that does, it assumes that everything diffuses very rapidly through our compartments. So basically, inside the cell, there's no gradients in this model, okay, of species. So this is sort of the more rudimentary. This is where you would start, sort of thing. Later on, you can define structures, and you can introduce what's called reaction diffusion systems. So where things diffuse and react. So anyway, so what we're going to do is we're going to, after we've told the model what our molecules are and define the basic structure, physical structure, we're going to define how the species interact. And as we do that, we're going to take just a rough guess on our reaction constants. Then there's an area you can use called observables, which is to say, let's say I want to watch a complex of molecules. Say I want to watch LuxR complexed with this O3 SHCl. That's a species that we can monitor, and which is different from it's a species which is composed of several molecules. So we can define those observables, and we can measure them in our model. So then we'll create the application, we'll run the simulation, have a look at the results, and then we'll find mistakes. And we'll try to refine our reaction constants and maybe look in the literature and see if we can get better ones. And then you sort of iterate through this process. And then at some point, if we're lucky, we'll come to some solid conclusions about how it's all working. So let me switch back. So, okay, let's go to molecules. Okay, now, one molecule for sure, click on new molecule. One molecule we know for sure we want is PFAS. Okay, let's add PFAS. We know, let's do all our proteins. So what are our proteins? And I will make mistakes, so correct me when you see me make a mistake, okay? So we know LuxR is a protein. We know our main reporter, well, let's do Lux. So we got LuxI, which is an enzyme which catalyzes a reaction. We have GFP. That's our main reporter. So that's our output. Okay. Let's see. We got any other proteins?
The AHL molecule, the really long
what?
name, the quorum sensing really long name one.
Oh, that's the that's not a protein though. That's the 3-OCH. Wait a minute. Not letting me switch my slides.
30C6HSL, right?
Thank you. It's what? 30. Say it again.
30C6HSL.
C6HSO. It doesn't like VCell doesn't like it when you start these particular molecule names with numbers. So I'm going to put an underscore there. Okay. So that is just a big organic molecule. It's not actually a protein. At least that's my understanding. Okay. So let's see. So that's our proteins. Now, the other thing we're going to want to do is to simulate our mRNAs. There are some models that you would just say, okay, I got a gene, and it's going to make this protein. And I'm going to go straight from gene to protein. But in this case, because we want to, really model a dynamical system that where the presence of the mRNAs is going to be important, we're going to put the mRNAs in. So we got, we got a LuxR mRNA, okay, and LuxI mRNA. And we've got a GFP mRNA. Okay, so those are all of our mRNAs, right? So now, of course, the DNA is a single molecule, but what we're going to do is VCell doesn't really have a good data structure for genes. But what I want to do is take each of the operand, or each of the sensors, each of the genes or operands, and represent the promoter with a separate molecule. So of course we got our very important prmA, prmA. I'm going to call it an operand. Okay. We've got our the computer's getting a little laggy. Dude, can I delete it? Yes, delete it. Like not letting me change the name all of a sudden. Okay. That's weird. Suddenly I can't change. It's already being used by an observable. Over here to observables. This is a little quirk. It creates an observable for each molecule by default, and you have to delete the observable before you can delete the molecule. Oh, this is fun. Darn it. Delete. Yeah, okay. Just super laggy. Yeah, I guess I'm just being too impatient. That's what I get for having 15 windows open. Let me try and kill a couple windows here. All right. I'm going to try to stop sharing for just a second and see if that frees me up. And it did not. Shoot. Let me try and kill off a few more processes. Okay. Let's see if this freed up anything. Good. I'm going to try and kill PowerPoint. Okay, let's see if that does anything. Nope. All right. I'm going to kill VCell and restart. Let's see if I can save it first. Let's do. Let me go ahead and share again. Yep. Sharing that window. All right. So I'm gonna go ahead and try to save this and see if this. All right. It's frustrating because just like some of the inputs are not being taken. So I'm restarting VCell. All right. I'm gonna try and load the model again. And you'll see when you open a model, you have your own little database here, and there are models that you can that are sort of public. There's all sorts of tutorials under here, and but there are my biomodels, and I save this under iGEM. Under each model or each simulation, you can have different versions. So I'm gonna go ahead and open this. Go back to my molecules and yay, okay, we're back in business. So let's see. So what is our other operand? So there is of course a LuxR operand, but I'm not going to worry about that because it's constitutively generated. But let's do the LuxI operand. Okay. Let me open up PowerPoint again. So I can check our parts list. Okay, so is there any other operands? Let me take a look at my parts list. So we got our mRNAs. Okay, so what I do want to do is I want to make a, I think I'll just call it the LuxR gene. And what I'm doing is I'm setting the simulation up so that we can run it a couple of different ways. So I'm setting it up so that we can run it as a set of differential equations, and we can run it as what's called a stochastic model. Okay, where when you have a very small number of molecules, like you have one gene in many cases, sometimes the sort of continuous approximation that differential equations makes isn't accurate because you have so few number. So the differential equations will represent all the species in terms of concentrations. Well, it's possible for you to be below a concentration which is like 0.5 molecules or 1.25 molecules. And in reality, that doesn't happen, of course. So I'm going to set this model up quite intentionally so that we can run it using a couple of different types of mathematical frameworks. So we got the LuxR gene. Let's see, we got our proteins. I do want to add, I don't know if you can see my slide. So I do want to add that there is a precursor, there's a set of precursors to this 30C6HSL. Because that molecule doesn't come from nothing. So I'm going to add that. Okay, and maybe I'll just say it's free. Okay. Let's see, what else we got? So we're going to have a number of things degrading. The proteins don't last forever. The mRNA don't last forever. And it's very important that they're metabolically turned over. So I'm going to create a couple of variables or species to dump my degraded products. That way we can sort of keep up with them in the simulation. So degraded mRNA, and I'm going to dump all my degraded mRNA into that one variable. Let me double check that. Yeah, we can do that. And here I didn't put, but we need degraded protein. It might be nice to keep track of which individual proteins are degrading and the rates of degradation. So maybe we could put, let's say, let's do LuxR degraded. A LuxI degraded. and a GFP degraded. Okay. All right. So I think that's, yeah, are we missing any parts? Let me go back and look at the, where's the cursor? So I'm overlooking the RBS. You know, that's going to be sort of subsumed in the model. We don't have to explicitly treat that as a species. So we got our two basic operons, prmA and pLux. All right, so we're good. Now we got to think about in VCell, you can represent different states of the molecule. You can represent binding sites. Of course, you know, we're going to have lots of things binding to different things here. So let's see, the first one is LuxR. So what does LuxR bind to? What is it? Yeah, someone can one of you guys answer that?
The 303.
Wait, does my mic work?
Yeah, I can hear you.
Oh, okay.
All right. So what I'm going to do?
Simulate RNA polymerases and ribosomes, or no?
Nope. So that's a great question. So we can add as much detail as we want. But right now we're going to keep it high level, and we're going to say those molecules that are ubiquitous, they're just going to be sort of in a pool of molecules that we're not going to explicitly treat mathematically. Okay. That includes your tRNAs, your ribosomes, all that stuff. Okay, sort of the ubiquitous machinery of the cell. You could add that, but for tractability and just to keep it somewhat simple, we're just going to stick with these.
All right.
So LuxR, yeah. So it does a couple of things. And it's not, yeah, there we go. So this is going to be the binding site for the underscore 3. Well, I don't know. Maybe I don't have to put an underscore here. Let's see. 3OC 6SH HSO. Doesn't like that. I got to put that underscore in there. So you right click to rename that. So this is 3OC 6. Okay, so that's where that molecule is going to bind. Now, what else does LuxR do?
It binds to the
pLux.
pLux. Yeah.
Yeah.
Yeah. All right, so let's add a binding site for that. Okay, so I think that's pretty much all we need for this. All right, LuxI. See, what does that do? What is the function of that?
It produces the quorum sensing molecule from the precursor.
Right. So does it bind to anything?
I would assume it binds to the precursor and then changes it.
Yeah. So it transiently catalyzes. There's actually two precursor molecules. So it takes two of these molecules and smashes them together, and there's a carrier protein too involved. But what we can do is just treat this as something that it's just a chemical reaction that happens. Okay. So and I'm gonna let me open my other more developed model, just so I can refer to it and make sure that I'm building something close to what I've already built. Okay. So we got degraded mRNA. GFP. Okay. I'm just flipping through my. So, okay. So LuxI, so we don't really need to define specifically any binding sites. We're just going to treat this as an enzyme that just catalyzes a chemical reaction. And you'll see what I mean in a minute, a little bit better. The other thing that I forgot to add was the action. Oh, let's see. We did get LuxR gene. And we need, we got the mRNAs, got those. All right, I think we're good. Okay, so anyway, so GFP, does that bind anything?
Not that I know of.
No, I don't think so. This doesn't bind anything. Now, we know the mRNAs are going to get bound by a ribosome, but again, we're just going to treat that reaction as sort of, it happens really fast and it sort of happens automatically. And we're not going to treat the components that the ribosome binding and all that stuff. So we're going to skip those. So the prmA operon, of course, needs to get bound by the promoter, which in this case is going to be, so it's going to be bound by some messenger that turns it on. Maybe I'll just call this messenger. So I'm creating a binding site, messenger. And so kind of the way we can think about this is that we have some PFAS. It does something to the membrane, and there are some messenger molecules generated that eventually end up hitting this operon. So there's a big question.
No, yeah, that's most likely what happens, yeah.
Yeah. So, but we don't know. There's a big question mark in between PFAS and the prmA operon. So the way I'm going to treat it, which is not correct, is that the PFAS is going to bind and turn on the operon. Okay, this is just a matter of convenience. Okay, and so it's an approximation. And we can improve this later on as we come to an understanding of what those steps are. So LuxI operon, my cheat sheet here. So LuxI, don't think we're going to need anything to find that. Hey, I think we do need something. Oh no, yes. LuxI. So what binds LuxI operon?
The LuxR, I think.
Yeah, dude.
The complex between LuxR and the quorum sensing.
Yeah, exactly. So LuxR has to have the quorum sensing molecule before it binds to the LuxI operon. So let's go ahead and let's just call that LuxR binding site. Okay. LuxR gene, yes, there's stuff that binds to it, but in this case, and bear with me, we're just going to treat it as, since it's constitutively produced, we're not going to worry about binding. No binding here. We don't have to worry about our degradation products. Okay. I think we're good to move on to the next step. So we might need to add some things later as we proceed through the model if we've forgotten anything. So the next big thing is structure. So you can have a number of compartments in your model. And but for simplicity, we're going to just have two compartments. We're going to have the cell, the interior of the cell, and the environment. So what I'd like to do is just call this first compartment environment. And then we'll add a second one. Call it the cell. Okay. So, of course, in eukaryotic cells, you could have really complicated, multiple, you could represent each organelle, the nucleus, mitochondria. You could get really wild with the number of compartments. And as I said, you can turn it into a spatial model. So where you have reaction diffusion things happening, but we're starting simple. So now this is the fun part. So click on reaction diagram. And let's start adding some species. So you see this little green circle is our species tool. I know for sure in the environment, we are going to have PFAS. That's the big one. Okay. The other thing we're going to have is our quorum sensing molecule. Oops, she made an extra one. Okay. Now, I should say this is free software, and you sometimes get what you pay for. Sometimes it's kludgy and awkward and will fault out. So this is our, so this 30 that about, all right, so 30C6 HSL. Okay, so that molecule can come from other bacteria around it, right? And in principle, experimentally, we could consider, delivering this molecule to our culture and seeing what happens. So that's something we might, nice variable to have. So the other thing is, let's see, let's start with we're going to create a new species in the cell. And I would say that probably the first thing we need to do is think about our constitutive LuxR. So let's call this new species inside the cell. This will be our LuxR gene. Okay. Oh, something I haven't done is you see down here on the bottom of the screen, a little green dot. I've got to tell it, no, I'm calling it a LuxR gene, but I haven't told it what molecule that actually corresponds to. So I'm going to right click on that little green dot, and I'm going to call it our LuxR gene. Okay. So you do that because each species, like I said, could be composed of a complex of other molecules or molecules with different states and things like that. So similarly, we need to go back and sort of define the PFAS in the quorum sensing molecule. So again, select PFAS. You have to click on the arrow, the select tool in order to select it, and then right click down here and specify that this is the PFAS molecule. Okay. Similarly with quorum sensing, go down here and tell it that this is that molecule. Okay. So now we're getting ready to do our first reaction. So what I'm going to do is I'm going to click on the reaction tool, that little arrow thing. I'm going to draw a reaction. Okay, so that is reaction 0. And that reaction is going to go to a product. Okay, what's the product of this reaction? You guys tell me.
The LuxR protein?
Yes, sir.
Okay.
What's our 13? Okay, and while we're here, let's go ahead and tell it what molecule that corresponds to. So I think we just called it LuxR. Okay. Now, now our first chemical reaction. All right. So when I click on the reaction, you can see that J here, the variable J in this table, that is the reaction rate. So that is the amount of Lux protein generated per second. You can see the units over there on the right. So it's the number of micromoles per second of LuxR protein we're making. And that is equal to the forward reaction rate times the amount of LuxR gene minus the reverse reaction rate where the LuxR protein turns back into the gene. Now, we know that proteins, oh, wait a minute. I've already made a mistake. It's not the LuxR gene doesn't make the protein, it makes the mRNA. So, oops. Let's rename that. mRNA. Okay. And I better redefine this. So I'm going to right click, specify LuxR mRNA. Okay. So, so now we got to think about reaction constants. So this type of mathematical treatment is called mass action reaction kinetics. I'm sure you guys have probably heard of it. It's sort of the most fundamental mathematics you can use to express chemical reactions. All right. There are lots of more complex mathematical treatments. There's the Hill function. There's Michaelis-Menten, which describes enzyme kinetics, right? For reasons that will become apparent later, I'm going to treat all these reactions as mass action. Well, I'll just tell you, the reason is because there's a little bit of a shortcoming in the software where if you want to do a stochastic model, that you have to have, you can only use Michaelis-Menten kinetics. Okay, so. Okay, so we have to ask ourselves a question here. The forward reaction rate. So at what rate do we make LuxR mRNA? So what's a reasonable number? Do we make 10 a second? Do we make 2 a second? Do we make 0.5 a second? So somebody think about it and give me a number. That's micromolar per second. And I would say the sort of default volumes that we have here, I think it's 10 to the minus 8 micromolar is roughly equivalent to 1 molecule in the cell. So, okay, I'm going to throw a number out. It kind of doesn't matter right now. Let's do 4e minus 4. Okay. That's a pretty low rate. But you'll see later on when we actually build a stochastic model that we will be able to switch between number of molecules and concentration really easily. And that will help us like really say, get an intuition for, oh, there are 400 molecules of LuxR in the bacteria. Okay. So from there, what does our LuxR mRNA do next? Well, obviously there's going to be a reaction, right? So the product of this reaction, so if we know we're going to make a protein with it, right? So when we make the protein, nothing happens to the mRNA, it's still there. So we should have an input to the reaction, which is the LuxI or LuxR mRNA And the outputs should be the LuxR mRNA plus the protein. So let's try and do a reaction like that. So I think I'll go ahead and say, instead of just using the arrows to define the species, I'm going to click here and add a species. And I want this to be our LuxR protein. Okay. And again, we're going to get our LuxR mRNA back. Oops. Now, when you're building these models, try and keep things readable. But the product coming out, like I said, we're going to need another, and the mRNA's got to come back. You see how I did that? I just kind of drew that arrow back to the LuxR mRNA. Okay, now we're violating mass conservation. So that's something to kind of think about. So, you know, in a sense, the LuxR protein just kind of appears out of nowhere with no precursors. So, but we don't have to worry about that too much. So what else? Okay, so now we got our LuxR protein. So what does it react with? Let's put the species. So
quorum sensing one.
Yeah. So what we want. So LuxR protein is looking for the quorum sensing molecule, and it wants to bind to that. So let's go ahead and underscore 30C6 HSL. Okay. Didn't like that because I already have. Oh, you know what we need? We need to transport the molecule into the cell. So, well, why don't we call this underscore 30C6HSL inside, okay? And let's rename this one. Let's call it outside. Okay, don't like spaces. All right. Now, it's going to be transported through the cell wall or membrane and into the cell. Now we know that because we've all done our homework that this molecule readily diffuses through cell membranes. I mean, that's what makes it a good quorum sensing molecule. So what we're going to do is we're going to treat its diffusion into the cell as just a reaction. Okay. Oops. Do that. And the reaction is just being transported into the cell. So I'm going to take this reaction and connect it to inside. So we got our second reaction. So go to the selection tool, select the reaction. Let's call this 30C6HSL transport, something like that. For some reason, it's doing. It made this kinetic reaction type as general. I don't want that. You can define your own math for some of these reaction types. It is possible to do that, but let's just stick with mass action. So this is basically going to be the rate of flow into the cell. How many per second? How many micromoles per second? So I don't know. It doesn't really matter. One micromole per second, I guess. We're going to come back and sort of tune these variables over time. Now, do you suppose it selectively holds the stuff in the cell, or does it freely diffuse out?
I have a
And so what?
question.
Yeah.
When you put the LuxR protein back to the LuxR mRNA, how come like you didn't get like the reaction square thing?
The reaction square. What do you mean?
Like
Okay. So it's one reaction. You mean right here? Why didn't I get a second reaction?
like yeah, like how come like when I tried to redraw it back, I have like another reaction there.
Make sure that when you use the little arrow thing,
Uh-huh.
the connection tool there, start on the reaction and end on the actual mRNA.
Okay.
Now
Wait, why
you can
is
of
there
course
an
just,
error that goes back to the mRNA?
because after the reaction, the mRNA is still there. Like
Yeah,
if we didn't have it going back to the mRNA, it would be like the mRNA was consumed in the reaction
Oh, okay.
and we would lose it.
Okay.
So anyway, and we should probably don't forget to name your reactions meaningful things, because later on it'll just make working with them easier. So I think I'll call this reaction make LuxR. Okay. All right. So anyway, now that we've got the quorum sensing molecule in our cell, we know LuxR wants to bind to it. I'm going to take the connection tool and do a binding reaction. Okay. So now we have to ask it. Let's see. Bind. I'll call that quorum binding. So now this, I guess that these constants in the model, the developed model that I have, and this information should be readily available somewhere in the literature. As popular as the system is, these must be very well characterized somewhere. Now, I haven't bothered to look, but that's maybe some homework. So, how many per second are we binding? So I don't know. Let's try. Let's try one. Yeah. Does it unbind? Does it ever release? What do you guys think?
I don't know. That was never really described. But probably. I'm gonna check.
So most proteins that bind something will have some reversed reaction rate. So at some point, the molecule can get knocked out. So I'm just going to say maybe it's 0.01. Okay. So it really likes to bind it, but every once in a while it'll let it go. Okay. All right. We can refine this later. All right. So what's next? So now we've got LuxR. It's captured the quorum molecule. So what's the next reaction? Where does it go?
The pLux promoter.
Yeah. So it's going to bind the promoter. All right. So I'm going to call this reaction pLux bind. pLux operon bind. Okay. Because it's not binding the protein, it's binding it. Okay. So, and of course, again, I've kind of forgotten to define the exact species. So this guy is going to be pLux operon. Okay. And I'm going to tell the model that this is the PLux operand. Oh,
Wait, shouldn't it be, so is the
yeah,
pLux operand the product, or shouldn't it be like the bound pLux operand as the product?
yeah. You're right. You're right. You're right. Let's be like, yes, you are 100% right. So we want it to bind. And I'm trying to, sorry, mRNA, searching pLux operand. I kind of named it poorly.
Yeah.
Well, I guess.
Well, I mean, it's the concentration of it
Okay.
doesn't really depend on anything that we're doing here. So we could maybe just use what we already defined.
Right. So yeah. Now this should be the product of this reaction should be a complex. So I've made a mistake. So let me delete that reaction. So I've got the pLux operand. It's going to go. So the inputs to this reaction are going to be the LuxR protein in the pLux operand. Okay. The model will stretch when you move things around. And so, okay.
Well, don't you need to define
Oh,
a separate like complex between LuxR and the quorum sensing molecule, and that will be the reactant to here?
so that's what we did here,
Is it? Oh,
right?
okay. Yeah.
So, while we're clicking on this, let's actually specify that complex. Okay. So I'm gonna right click on that product. Oh, you're right. You know what? We need a separate species, don't we? See, this is why it's like the process of building this model will help you really understand how step by step how everything works. So yeah, I told you guys I would make lots of mistakes, so shouldn't be surprised. All right, so I'm going to click on that line and be like, oh yeah, goodbye. Going to delete that line. So, well, first of all, so this is. Oh, see, I've made a couple of this.
Yeah,
All right.
that makes sense.
Yeah. So the way I have this reaction written is it looks like the quorum sensing molecule transforms into the protein.
Yeah.
Which it does not. Okay. So yeah, I'm going to delete this reaction too. Okay. So what they do is that they come together in a reaction and they form that complex. See what I've done?
Yeah.
Okay. And then we come out of there and we will form. Okay. So this species then, the specified molecule, it's definitely the quorum sensing molecule or the quorum molecule. And I'm going to right click just to the right of the quorum sensing molecule. I'm going to specify another species, and this is going to be our LuxR protein. LuxR protein. Okay. Oh, that reminds me. I've made another mistake. So we need a binding site for the quorum sensing molecule. Okay.
Oh, okay.
Because we want to connect these two. Okay. So we'll go back, go to molecules, go to the quorum sensing molecule. I'm going to right click. I'm going to add a binding site. Rename it. LuxR. Okay. And going back to the reaction diagram. Now back to our product. All right. So Oh, shoot. Damn it. Not Lux. Yeah, that's right. Okay. So if I click on this species, I can tell it what site they're going to bind. Okay. So I right clicked on the LuxR and say, it's going to bind to this site. Everybody see that? Okay. So that is my product. It's the bound quorum sensing molecule with LuxR. Okay, let's see. Also, now the LuxR protein, I haven't told it what molecule that is. I'm going to specify the molecule. That is, of course, LuxR with 2 unbound sites. I haven't labeled this molecule. We got to tell it down here, this is the 306C6HSL. Okay. Okie dokie. I hope I haven't confused you guys too badly, but really, this is kind of how it goes. You're like, oh, this does this. No, wait a minute, that's not right. All right, so we've got. I'm gonna call this species LuxR bound, I guess. Okay. So pLux bound. Now, finally, this can go to. I'm gonna delete this species. So our LuxR with the quorum sensing molecule will now interact with the pLux operand. Okay. Is that intuitive? Everybody following along? Okay. So now we got to think about our reaction constants. So technically, the bound LuxR is going to stick to a piece of DNA and turn it on. Yes, there's a bunch of molecules involved, and I'm kind of glossing over the complexity of the situation. But basically, we want to ask, with what affinity does the LuxR bind that piece of DNA? Is it a strong promoter? Is it a weak promoter? So the higher the forward reaction rate, the more, the longer it's going to stick to that piece of DNA. And the way I'm going to represent it is that the longer it sticks to the DNA, the more of the product we'll see. Okay. Now there will be a separate reaction constant for that, for the production of the protein, but I don't like the direction of this arrow. I'm going to delete this. Yeah? Question? No, I guess that was the right direction. All right, so. Oh,
Actually,
yes? Okay, so what is this guy? This is.
That'd be GFP. Oh, or no, that would be the promoter.
Yeah, so sorry. I guess I did have it right. I'm second guessing myself. pLux operand. Okay, so they're going to come together and form a complex. Out of this reaction, we have a product. So the product is going to be LuxR with quorum sensing molecules sticking to that piece of DNA. So bound pLux and LuxR. Okay. So again, this is, so the promoter is going to stick to that piece of DNA with some affinity, let's say 0.01, just pulling a number out of the air right now. Now, at some point, it's going to come back off, right? Promoters don't stick to pieces of DNA forever. So we're going to give it some unbinding rate, say 0.01. Okay. Okay. But now, while that promoter is bound, we're going to make a protein. Let's look back at our construct. So our construct is here. So here's our pLux. And what does pLux make? It makes GFP. So that's our output, right?
Mm-hmm.
Okay. So we're going to need another reaction. While that's bound, it's going to go ahead and make a protein called GFP. The reaction I'm going to call make GFP. Let's put that 1. Now, when you make a protein, do you ever unmake a protein and go back to the DNA?
No.
No.
Wait, should it be the GFP mRNA, or do you just want to skip that?
No, you're right. I was just going to say, oops. All right. So maybe let's call this make GFP mRNA. Okay. Now, again, we don't go from mRNA to DNA very often. Only certain viruses do that. So the reverse reaction, I'm going to set at 0. That just doesn't happen.
Yeah.
Okay. All right. So what is our species? This is the mRNA. So this is GFP mRNA. Okay, don't forget, we got to come down here, specify the molecule, GFP mRNA. Now, this is going to be important because, cells, tightly control mRNA. It doesn't last forever. You wouldn't want mRNA floating around your cell forever because the cell has different needs at different times. So, all right. So now, obviously, from the RNA, finally, we'll make the protein. I'm going to call this new reaction make GFP protein. Okay. So the mRNA is going to be pretty transient. So how quickly do we make proteins from mRNAs? How long does it take a cell to create a protein? I mean, obviously, it depends on the size. But just generally speaking, do you have a sense of how quickly that might happen? So if you have 1 micromole of GFP mRNA, how many micromoles of protein would you make? So I don't know. If Douglas, if you find the number, tell me, or if anybody can Google, tell me. Otherwise, I'm just going to put a placeholder.
Oh, it says 20 amino acids per second, which depends on like the size of the protein. So
yeah. So I don't know. Let's say let's say 0.1 micromole. And obviously, the protein doesn't ever get turned back into mRNA, so there's no reverse reaction.
Yeah.
Okay. Selection tool here. Okay. Oh, push it back. Okay. So So we're making the protein. We need the product. Product protein. It's really annoying that they don't let you select with that same tool. Okay. So yay, GFP, our final output.
Oh, wait, there should be like another arrow that like goes back, right? Because it doesn't get consumed in the reaction.
Good call. Yes, absolutely. Okay. So let me define this molecule. GFP. All right. So all the little green species have not been defined. So let me just go back and so this product is.
Do we have one of those? Or?
So we've got our LuxR.
Okay.
It is bound to the quorum sensing molecule.
Mm-hmm.
Thus, no, wrong. That's the wrong way. This way. Okay. But it's also bound to the operon. So now we've got three things going on here. So, so this is the LuxR. Okay. So now we've built this complex, this 3-molecule complex.
Nice.
Okay. So let's see. So while that is there, it can make the GFP mRNA. And let's see, do we do have some reverse rate? Of course, all the mRNAs and the proteins will degrade. So we haven't done those reactions yet.
Mm-hmm.
So
also, I was gonna say, so in like a very realistic scenario, even like an unbound promoter will also be transferred.
it kind of dropped out.
Huh?
You kind of dropped out there. Even an unbound promoter will produce
I think it'll
a product.
still transcribe, just at a very lower rate.
Oh, interesting.
Because that's leakiness.
Right. Okay. Let's worry about leakiness later.
Okay.
It's a really good point. So let's see. So we haven't dealt with, looking at our construct again, we haven't done anything with PFAS so far. So let's think about that reaction. So we know we're going to sort of hand waving model the PFAS turning on the prmA as a binding event. Okay. And then we'll have it produce a LuxL mRNA or LuxI mRNA and then a LuxI protein. Yeah. And then LuxI is going to catalyze the formation of the quorum sensing molecule.
Mm-hmm.
So let's take care of that. I'm going to move these guys up. We'll do all our PFAS stuff on the bottom here. So again, we got to have PFAS get into the cell.
Mm-hmm.
We can go there. And it is all the product of this reaction PFAS inside. Yeah, this is kind of, again, so I'm clicked on reaction 2 here. I'm going to switch us back over to mass
PFAS
action.
also has a binding site, right?
Yes, I think you're right. Yeah. All right, let's go fix that. Go back to molecules, PFAS, right click, add site. Just call it bind, I guess. Okay. All right, so let me define this PFAS inside, tell it what molecule it is. It is PFAS. Let's set our reaction constants. So this is kind of an interesting thing to consider is the PFAS, how quickly will it get into a cell and signal, that there's a problem that we need to turn on the quorum sensing molecule.
Yeah.
So that's what this constant sort of represents. So I think let's see, what did we use for quorum sensing? We used 1. I'm going to bet PFAS is a little slower. Let's just say an order of magnitude lower. Okay. And how readily does it escape the cell? If we don't let it escape, the concentration might just build up in there,
Mm-hmm.
So let's put some sort of reverse reaction rate there. So 0.01. I feel like most PFASs have pretty strong affinity for membranes, and probably when they have a strong affinity for certain proteins too. I was reading about that the other night.
Really?
But anyway, actually, they stick to in blood samples.
Mm-hmm.
PFAS sticks to blood albumin
Oh.
more than LDL or HDL. You would think it would stick to the fatty acid carrying molecules, but apparently it has a greater affinity for albumin. Funny thing about that study was that they just took a group of random people and tested them for PFASs, and they found it like all over.
Yeah. Yeah, that's crazy. Yeah.
It was kind of wild.
Mm-hmm.
All right. So, okay. So we got our PFAS inside. PFAS is going to bind to what?
The pRmA.
Yeah. So reaction 3 or product is going to be, oh, wait, I'm setting this up wrong. No, I'm not. No, I'm not. So this is specify the molecule. This is prmA operon. Okay. And we do have a nice site for our messenger to bind. Yeah, I did set this up wrong. So these are our 2 inputs. PFAS, prmA operon are the input. The output is the complex. So let me switch that arrow direction here. Let's go that way, and here's the product. Okay. So S12 here is going to be prmA operon. I haven't named it. prmA operon. And the product is going to be our PFAS molecule and our pRmA operon. And you're going to right click and tell them specify the bond. Bound. pRmA. Let's do this. Okay. So now the bound pRmA, that's a big signal. So looking. So when pRmA is activated, out comes LuxI. LuxI mRNA.
Yeah.
So we're going to do this. Now, the other thing is that, well, let me put the product first. Okay, here's a product, which is going to be LuxI mRNA. Okay, specify the molecule. Now, how quickly are we going to make this mRNA? How quickly did we make GFP? We said 1. Right.
Mm.
So, and again, there's no reverse reaction because mRNA is not going to turn into the bound complex again.
Yeah.
Okay, so this reaction I'm going to call make LuxI mRNA. Okay. So we got to be careful here, because
I just realized for like the bound Lux and the bound prmA, we should also have an arrow that goes back, right? Because it's not consumed in the transcription process.
you are correct. I was just about to say that. Okay. So then we got our mRNA, and we made that same mistake with this.
Mm-hmm.
Yeah, let's fix that one too. Yeah. Okay. All right, and LuxI, of course, is going to make the protein.
Mm-hmm.
There's a protein product. So LuxI protein. Okay, and we'll specify the molecule. LuxI. And as before, the reaction should come out. The LuxI mRNA. Okay. Okay.
Nice. What was the rate of translation that you put?
We can just do something similar.
0.1? I don't know.
Yeah, 0.1.
Okay.
Okay. All right. I think we got, so now we've got the LuxI protein, the LuxI enzyme. It's an enzyme that catalyzes a reaction. So it catalyzes the formation of our quorum sensing molecule.
Yeah.
Oops. Back. Okay. Got my arrows pointing the wrong way here. Okay. So this molecule is the quorum sensing molecule. Yeah. 6 HSL. Okay. And we need the precursor molecules as an input. Uh, Precursors. Okay. And we have a molecule for that. That's it. Let's go down here. Okay. And it goes, it's an input to the reaction. And also coming out of the reaction, we still have the protein. Oops. Right. Okay. Let's see. Constant, forward constant. It's probably not going to run backwards very well. So I'm just going to leave that at 0.1. And let me name this reaction. Make. Okay. Alrighty. So, how are we doing on time? Our audience has dropped off. How are you doing, Douglas, on time?
I'm doing great. This is great.
Okay. Okay. So, water. We're getting close to actually running the model.
Yeah.
We
Wait,
could.
For the final quorum send, can I just like draw another arrow to the other one that was using it that way? Okay.
Yeah, you could. Absolutely. Absolutely. Yeah, that's very absurd. Okay. So we could run this model now, but nobody's degrading. So all the species would just accumulate and it would be very unphysical. So let's degrade some molecules. So all our mRNAs are going to degrade. Okay. I know this is tedious to start with, but the payoff is pretty significant. And it actually can be fun, particularly once you got the model running. So LuxI, mRNA degradation. Now that's something else we could ask ourselves. Well, how quickly do mRNAs degrade? So
like tightly regulated too. There's like regulation methods for that.
Yeah, I mean, there's a reasonable window.
Yeah.
That it's maybe minutes to hours. So that at least gives us sort of a ballpark. But for now, let's see. Let's say let's give it 0.004-ish. And obviously, it's never going to undegrade. Okay, so the reverse reaction is never going to happen. Straighten this out. Okay, so and I have a species for this, so this is degraded. LuxR. What we're going to probably find, and the model that I've already developed seems to.
Oh, did he leave?
Yeah, he left.
Oops. Oh no. I guess I take over now. I don't know. Draw errors.
Can you hear me, Douglas?
Yeah.
Okay, while we're waiting, are you guys are planning on going to Paris or not?
If we do go to Paris, then I think everyone has to pay themselves because,
Okay.
yeah.
So what? Well, it's back on.
Oh yeah. We could talk later. I do have to go at 12. So, oh no, but
Okay.
You're 3.
Yeah. Sorry. It turns out that when I press my the button on my headset here, it disconnects the call.
Oh.
I was trying to scratch my ear, and it disconnected the call. All right. So let me share my window again.
That's interesting.
Okay. So so we're doing degradations. Let's just protein will degrade. I'm going to try and speed it up a little bit because I want us to at least get to running a model, even one with terrible constants. So this is LuxR. LuxR protein degrade. Okay. And this species is going to be so we got LuxR degrade. Okay. Okay, so we got those guys degrading. Let's see, we need LuxR. LuxR bound will also be degraded.
Will it?
So
or, wait, would it be like specifically degraded, or would it just be a reversible reaction such that the protein gets degraded?
you know, that's a good question. I'm not sure. I don't feel like if there was you know, a cofactor that the cofactor would prevent a protein from being degraded.
Yeah.
But we can just leave that. We can leave that blank and see how it works out. Okay. So GFP mRNA is also going to degrade.
So I just put like 0.004 for the rate constant.
Yeah, that sounds good. 0.004. And species. That is GFP degrade. Wait, did we have one specific for mRNA?
Not for degraded mRNA.
Okay. All right. So just degraded GFP. Okay. Okay. The protein degrades. Let's see. Let's make sure we got all our mRNAs. There's another mRNA. LuxI mRNA degrades. 0.004. Okay. And this is specify molecule. LuxI degraded. Okay. Okay. All right. Protein degradation. So we did mRNA there. LuxR protein degradation. We did there. GFP degradation. Do that one. Let's see. What are we using for proteins? Did LuxR protein degradation. Oh, forgot to put in a rate constant for LuxR degradation. 0.002 maybe. Okay, GFP 0.002. Name that species. It is GFP. See. Just dump it all in there, I guess. So something we're going to have to be careful about is that I'm degrading the GFP into the mRNA, the GFP, mRNA, and the protein into the same species. So, but degraded. See? Degraded protein. Okay. Let's see. We got to degrade LuxI, which we did. All right. LuxI mRNA. LuxI protein needs to degrade. Okay. And let's see. Degrade. Okay. Okay. Specify the species. Degraded. Okay. Okay. All right. Now, have we forgotten any reactions?
I don't think so.
All right. Yeah. Okay. Sounds good to me. Now, if you click on the reactions on the top left, you'll see a list of all the reactions we built and their names. And some of them we forgot to name because we're running out of time. But it is a good idea to go through and name all the reactions. I'm going to click through and look for all zero rate constants. So like this one, PFAS inside plus PFAS. So it's going to have, I'm going to put that as a 1 and a reverse of 0. Okay. Okay. Here's another one. LuxI protein degradation. Forgot to put that. So we're putting that 004, I believe. That was, oh no, that's protein degradation. Protein degrades at a. Yeah, here's protein degradation. 002 is what we're using for protein degradation.
Oh, okay.
Okay, so you know how many? So we've got a lot of reactions. Okay, and each of these reactions is represented by a differential equation. It's a first order differential equation, if that means anything. It's just the rate is equal to a rate constant times the concentration of the reactants minus a rate constant times the concentration of the products is equal to the rate of the product formation. So anyway, and so there's a derivative on the left side of the equation. Okay, we got our structure, species. All right, let's try a simulation. Okay, so you go to applications, new application. We're going to do a deterministic application. Okay. So that deterministic as opposed to stochastic, which is sort of noisy and where you have individual molecules. Okay. So under applications, now we've got a bunch of selections. We could further specify the geometry up to and including microscope images that have been Z-stacked. So you can actually take real cells and take the system and put it into a real cell that you observed with a confocal microscope. So there's a way to do that, but we're just going to leave it without real geometry. So it's going to be, all right. So now this is where we put in our initial condition under specification. So our initial condition, let's just say 0.1 micromolar of PFAS. There's not going to be any quorum sensing molecule outside. We are going to have the LuxR gene. Now, obviously, there's one usually. You know, it is possible, of course, for constructs to have multiple plasmids, in which case there would be more than one copy. So I'm gonna do, let's do 1e minus 4 micromolar. Okay, that's a pretty low concentration. So that's 1 times 10 to the minus 10 micromolar inside the cell. mRNAs, you don't. Let's start with a few. Let's start with I don't know, an order of magnitude more than the gene can. 3. Okay. LuxR protein. It is important in this system to have LuxR protein present. You know, Douglas, this is kind of the problem with the models, that you got to have a lot of LuxR protein to get a good sensitivity to the PFAS. So it seems like you have to have a good pool of LuxR protein to get the model to work well, or the construct to work well. Okay, but let's go ahead and do. Let's do. Well, oh, I forgot to put a 1e minus 3. Okay, so let's go ahead and do, I don't know, we'll put in a lot, 0.1. Okay, we're not going to have any of that outside. So none. Oh yes, we definitely need one of those. That'll be about the same concentration as our other gene, -4. Okay. No Lux, no GFP, no PFAS inside. LuxR opera or pMRA opera, same as the other mRNAs. 1e minus 4. No bound. No LuxI, mRNA, or protein. Precursors. We need plenty of precursors. This is a ubiquitous set of ubiquitous molecules inside the cell. Let's put this 1. Sounds good. Now, we're not going to let those disappear. They're always there, so we're going to clamp that value.
Okay.
Okay. Degraded. Okay. I think we can give it a try. So now we go down to simulations. Okay, and you're gonna press the little plus thing there. And we are, so we're gonna run for, let's say, I don't know, let's give it like an hour, 3,600 seconds. We can edit the model, so it's going to report every one sample. The way the algorithm works, it sort of determines when things are changing quickly and it samples more quickly. So if you click on edit simulation, you can do things like scan parameters. Let's say I want to change reaction. I want to see what influence reaction constants have on the results of the model. And I could say, you know, step through a sequence of values for this model. But let's just go ahead and run it. The little green arrow on the top right is a run. So what this is doing is it saves it to the remote database. It's running on the University of Connecticut supercomputers right now. And look how quick it was solved. Okay. So you click on the simulation, go to the little graph looking icon, and it brings up results. Okay, so we had no quorum inside. Huh, that's not good.
Wait, oh,
Oh,
I had different numbers that kind of worked. Oh yeah, that works.
Yeah, so we did make the quorum sensing molecule, and this is also inside. These are just treated as two different observables. So we can fix that later. So let's see. The important thing is, did we make any GFP? Nope.
Oh,
Did we make GFP mRNA? Nope.
I-
So let's see. Did we make LuxI? Oh, we did make LuxI mRNA. So that's good. Did we make LuxI protein? Yeah, made some of that. So what about LuxR?
Hmm?
Did you find the mistake?
Oh no, or like for my, or first, well, did you, so we had like 3 like sub-circuits. Did you connect the one where we made the quorum sensing with the total amount of quorum sensing inside the cell?
Let's have a look. Go back to reaction diagram. Okay.
I don't think you did, maybe, I don't know.
So you mean here?
Yeah, it's not connected to like,
You're saying we should go back to just run it back to that?
I think, yeah.
Yeah. All right.
What I
Sounds
did
good.
was just have a reaction from that to that underscore inside, and then I made the reaction rate like 1000.
Okay.
I don't
sounds
think
good.
that's how you're supposed to do it. But,
That's a pretty big reaction rate, but
yeah, but like they're the same thing, right? So
yeah. So what I'll do is I'll just take the product of this reaction and
you could just do that.
just connect it.
Oh,
Am I supposed to get a pure black screen when I run the system?
what?
My screen went black.
Probably crash the servers or something.
I'm running mine locally and it's fine.
You already figured out how to do that. Okay, good.
Oh, I
So
think
yes. So if you hit the blue button, it'll run locally. Okay.
Oh, okay. Yeah.
But if you hit the green button, it'll run on their servers.
Wow.
So
How do I run it again?
Huh?
How do I run it again? The buttons are grayed out now.
Well, you'd have to make a
Oh.
change in order for it to run again.
Oh, I guess I did, yeah.
Which I did. Oh, that's weird. Oh, is it still running? That must be it. It's probably still.
No, I had to click on it and it works now.
Oh, okay. Anyway,
It's really interesting. I have a lot of degraded GFP. I had like 7 micromolars of degraded GFP and 0.7 of not degraded GFP.
Huh. So I got.
Oh no. Eric screwed up the rate.
So yeah, so this is good. But so we got a signal. So this is great.
Yeah.
So now let's real quick, because I'm gonna let you go in 9 minutes.
Mm-hmm.
Let's real quick see how sensitive this might be. So where is our PFAS and Nick. Okay, so let's scan that and a list of values. Let's go 0.01, 0.1, 1, and let's see how low we can go. 0.001. This is 0. Okay. So just click OK. And now it's going to solve the model for all those values. Okay, so let's see what we got. So again, this would be like doing an experiment for an hour. So degraded GFP, or I mean GFP total. So there's 0.001, 0.01. So you can see that the dynamics are indeed changing. So we got a lot. So our peak is, my peak. You may have different answers if you did different constants. It's like 0.46 or something versus 0.003. So quite a bit lower.
But like, if we're actually doing the experiment, would such a low value even be detectable?
Oh yeah, this is so the EPA is wanting parts per trillion.
Mm-hmm.
I think like 10, 20 parts per trillion or something like that. So
What I meant was like, would this low amount of GFP be detectable? Not the.
Oh yeah, that's a really good point. Well, yeah. I don't know. Fluorescence is one of the most sensitive detection techniques. So I don't know. That's now. First of all, bear in mind when it comes to particularly biological modeling, all models are imperfect. Some are useful. Okay, all models are flawed. Some are useful. So don't trust this until you've really kind of gone through all your reaction constants and think you really have something that's representative of what's happening in nature. And it would seem to me that, a lot of the Lux related operons and genes and all that should be well characterized in the literature somewhere. So if we could come back and put in reaction constants from the literature, then we'll have something more accurate. All right. So the utility of the model is to get you thinking about all the detailed reactions that happen and give you a qualitative sense of what things depend on one another. And when we have the real reaction constants, then we can maybe start and have done experiments. Then, and we're getting it to match. Then maybe we could consider the model a little more reliable. But we're a long way from that point, and we didn't get the stochastic stuff at all, unfortunately. I can show you a little bit. So just quickly, you can right-click on applications, go to new application, stochastic, okay? And it takes these differential equations and these rate constants, and it turns them into probabilities. So the rate constant now is represented as a probability of molecules undergoing those reactions. So let's do a simulation. Now you can see that the solver is something called Gibson. And let's look at our sort of initial conditions and such. So we're going to have to see at the top, we have concentration and now number of particles. Okay. We didn't have that before. Now everybody's molecules. So this to me is in many ways more intuitive. So let's say, we got a million PFASs. And we've got 2 LuxR genes. So we've got a plasmid. We got 2 plasmids in the bacteria. Let's give it a little bit of initial LuxR mRNA. Let's give it 10. Let's give it plenty. Let's give it about 500 of the LuxR proteins as an initial condition. Then we need our operons. We got 2 of those. We don't have prmA. Say we got 2 of those. None. Okay. So let's go ahead and go back to simulations and click on it and run it. Oh, shoot. I only got it running for 1 second. That's boring. Let's do that for an hour, as we did before. Oops. It's giving me a warning. So instead of it automatically picking the data points to save, it's going to pick specific. You have to tell it the time steps you want to save. So I'm going to do 2 seconds. Every 2 seconds, it's going to save the data. Go ahead and run it. Now, the bad thing about this simulation is that it runs a lot slower. So because it's keeping track of particles. We may have to, usually it's, yeah, okay, here we go. When you do a sweep, all right, so everybody's 0. So my GFP out is 0. Let's look at LuxR. LuxR protein. So we started off with a bunch. Oh, okay. There's also, now you can see there's speed, there's concentrations and counts in the data. Let's just get rid of concentration. I don't really care about I want to know the exact number of molecules. So, so where's my LuxR protein? So it makes it, we start off with a bunch of protein, but our reaction constants are now not sufficient to like keep a population of LuxR. So you would have to backtrack and see where that went wrong. So, okay, with that, I'll leave you guys be. Thanks so much for paying attention. And I hope some of you can walk away with a model that you can play with. Like, I mean, I stay up like all hours playing with these models. Okay. You know, it's pretty entertaining, I think. I guess I'm a little nerdy. So anyway, have a good Saturday, you guys, and
You too.
Okay.
thanks so much for paying attention.
Yeah,
Mr.
thank you
Zonzik,
so much
nice
for
to see you
showing
again.
this. I think it'll be
Sure.
really
Now play
helpful.
with it. Yeah. Now just goof around with it and see what you can make it do.
I don't actually have the full model because I was gone for an hour.
I can send you the file. I don't know.
Uh,
I can like just send him the file and he can open it, right? And it'll work.
Can you send
Um,
me it too? My file just died.
Huh?
My thing just died. It doesn't even open anymore.
Oh, file. Okay.
Pure black screen.
I'll just send the VCML file, whatever it's called, in the Discord.
Yeah.
Yeah.
All right. Bye.
And my black screen doesn't even want to close now. I can't even close it.
Ow. Okay.
So I wanted to mention you can share models. So I will make my model public, and you can, within the app, you can see my model. So it's it'll be on the bottom left corner where it says shared models.
So, do we look for your username or like a title?
Let me see. Look at the software real quick. So it'll be under public models. I will publish it. And yeah, I think it'll be, I have a couple models already published. Let me see.
Let me think.
Yeah, you see, it's really kludgy. Geez, where, let's try to search. Yeah, just search for seriously. And you'll see it under published. Okay.
Okay.
But I haven't published it. I'll publish it right after we get off the call. Okay.
Okay.
And I'll let you guys know on Discord.
Yeah.
Douglas, when do you get back from California?
27th.
Jeez. All right.
Yeah.
So it's in public biomodels, right?
Yeah. It will
Under
be.
uncurated, I assume.
Oh yeah, it would probably appear under uncurated. Yeah. Because so published is when you've actually published a paper.
Oh, I found it. I found your COVID.
Yeah.
Yeah.
So those are different things I did a while ago. I haven't shared this one. Oh yeah, I started playing around with the simulation of COVID and how it works. I wanted to do that as like a public science or a citizen science project, but I couldn't get any support for it. So, so it just kind of died on the vine. So,
can VCell do like gene expression?
I guess it depends on what you mean by gene expression. I said earlier, you know, there's no good like data structure for genes or a genome in this software.
Yeah.
And I wish they would add something, you know, and then sort of have inbuilt promoters and just sort of default reaction constants would be great. But no, you have to build it as a species, and where each one is, you know, like we did with each promoter in Operon.
Yeah.
So,
Okay.
anyway, all right. I'll leave you guys to it. I will let you know when I have it shared on Discord.
Yeah. Okay.
Okay.
Thanks for teaching.
Okay. See you guys later.
See you. Okay. Yeah, I gotta go too. Yeah, Mr. Swansik, do you have any questions that you wanted to ask? Oh, okay.